Hi, this is Daniel Wieland.
And this is Amanda Birch, and today we'll be talking about emission spectroscopy. In this process, a photoexcited substance produces a range of light emissions at different wavelengths. The wavelength at which the most photons are produced, or with the highest intensity, is called lambda max. The different intensities that are produced over a range of wavelengths are determined by how excited electrons return back to their ground states in molecules. Electrons in a molecule can absorb specific wavelength photons to achieve a higher excited energy state. As the electrons return to the ground state, they may move into intermediate energy levels. For each change in energy level towards the ground state, the electron emits a photon. The greater the energy change, the smaller the wavelength of the photons that are produced. The more often a particular photon is emitted, the greater the peak on the emission spectrum at that photon's wavelength. Every photon emitted plays a role in the emission intensity at that photon's wavelength, regardless of whether the emission of the photon brings the electron to the ground state. The energy levels available are dependent on the particular atom or molecule's composition. The greater number of pre-existing electrons found in larger atoms or molecules would allow for more potential higher energy electron configurations, as opposed to smaller, less electron-dense atoms and molecules. For example, molecules with lone pair electrons can absorb and therefore emit lower wavelength photons because it takes less energy to excite a lone electron to a higher energy state than it would to excite a more energetically stable bond electron.
This process can be modeled using sound waves instead of light. When someone plays the flute, they input a certain volume of air per second, which is analogous to a stream of light. This volume of air per second creates a certain pitch. This is the output of the system, or color. Although several frequencies of sound are produced by the flute, one dominates. This is the lambda max, and it is the primary influence on the color or sound produced. The other frequencies produced can shift the sound, but only slightly. The piccolo, however, is a very different substance. When the same stream of air is input into the system, a completely different sound is produced. This substance has a different lambda max and thus a different resulting color or sound, even when the same type and amount of energy is introduced. In molecules, this result can be explained because different molecules absorb different wavelengths of light from a light source. Likewise, the piccolo and the flute use different amounts of air because of different mouthpieces. Even if these instruments use the same amount and type of airflow, they would not necessarily emit the same wavelengths of sound because they are different substances. This corresponds to differences in energy levels, which can result in different emission wavelengths even in substances that absorb one of the same wavelengths. Most things in nature are made of more than one substance. When the sounds of these two instruments are combined, a different effect is produced. This sound is not the same as either of the two original sounds. Instead, elements of both are audible. Likewise, if two substances of different lambda maxes are mixed, there will be peaks on the emission spectroscopy graph at both original values. However, the combination of the two peaks produces a different observable output than either individual peak.
And that's how the lambda max produced in emission spectroscopy can be linked to color. Thank you for watching.